Welcome to the next lesson in this chapter, where we are going to discuss the modular architecture that we have built so far, and also what are some tools that we can introduce to help us enforce this architecture going forward. I mentioned in the previous lesson that using the compiler is the most cost-effective way to enforce your software architecture. You will get almost instant feedback when something is broken, and you will be forced to fix it before you can continue developing your application. And the only problem is that in C#, we have a relatively limited capability of how well we can enforce architecture rules by using the compiler. The main options we have are assemblies or separate projects for hosting our source code and utilizing the internal keyword to hide implementation details inside of these assemblies, but when you think about it, these tools are relatively limited in what they can do, and the worst part is it's very easy to bypass them if you really want to. Using assemblies and the internal access modifier, we can get some very good encapsulation inside of our modules, but the problem is, as I stated, that this encapsulation is unfortunately easy to break. At the start of our implementation of the Evently system, the first thing we did was introduce static code analysis, and this allows us to enforce code style rules inside of our codebase. There are a few static code analysis tools that you can use, such as StyleCop, Sonar Analyzer, which is the one that we implemented, and you can also write your custom Roslyn analyzers where you can impose some pretty interesting constraints. The only downside is they are very complicated to write. There are a few more complex tools that you can introduce for static code analysis and enforcing your design rules, such as SonarQube, NDepend, and NSDepCop, which I want to explain in a bit more detail. SonarQube and NDepend are pretty popular and also very powerful. I'm going to leave some documentation links under this video so that you can explore what they can do for you. And now let's discuss NSDepCop. It's a static code analysis tool that allows you to enforce namespace dependencies in your C# projects. It's available as a NuGet package, and it's very interesting what it allows you to do. You can write an XML file that contains your NSDepCop configuration, and here's an example of what that might look like for the Evently system. This isn't the complete architecture that we have, instead it's just an example, but it should be enough for you to understand what NSDepCop allows you to do. We can define the direction of dependencies between the namespaces using an allowed XML element, and then we can define the from and to values. For example, we can say that we want to allow a dependency from Evently application to the Evently domain namespace. We also want to allow a dependency from Evently presentation to application, as well as from infrastructure to application, and then from infrastructure to presentation. So this is a very interesting way for how you can define your namespace dependency rules. We can achieve the same with architecture testing, and that is the approach that I'm going to take. But I wanted to mention NSDepCop as a viable option for enforcing some interesting design rules. I'm also going to leave a link to the repository containing this library if you want to take a closer look. And now let's jump over into the code and discuss some of the strategies that we are using to enforce a modular architecture. First, I recommend that you download the latest version of the source code that's available right under this video, because in the background I introduced the attendance assembly and integrated it into the solution. And now let's discuss some of the techniques that we are using to implement our modular architecture. First of all, you can notice that our system is nicely logically isolated from the folder structure perspective into 4 modules. And all of these modules contain a very similar structure between them. They are following the clean architecture, and they all have a domain, application, infrastructure, and presentation projects. And then, because we decided to communicate between our modules using messaging, we also have an integration events project. Another rule or constraint that we have is that we don't allow references between the modules except through the public API. And in this case, the public API is the integration events project for all of our modules, and this is the only project that other modules are allowed to reference. The next thing that we are doing to enforce our modular architecture is information hiding or encapsulation. Let's take a look at the ticketing module, for example, and start from the domain layer. I will pick the order entity, and what you can see here is that we are trying to make things private by default. So anything that can be private is going to stay private, which allows us to encapsulate anything that we deem important, and we only expose the things that we need to the outside world using the public access modifier. Now, inside of our domain, we're going to need access to our domain entities and most of the properties, so they have to be public, but we are encapsulating the behavior and the internal implementation details into our domain entities. If we go over to the application layer, and let's take a look at the use case for creating an order, for example, you will see that it's internal by default. The same applies for the respective command validator, and this is because we don't want to expose any implementation details outside of our application layer other than the things that really need to be public. And this only includes the command or the query for that matter, but essentially this is an entry point into our use case. We're also exposing any abstractions that have to be implemented by the other layers in our architecture, and this is taken care of in the infrastructure project. So let me close this down, and then let's discuss what we are doing on the infrastructure layer. Here I want to highlight the use of a dedicated database context for each of our modules, which allows us to encapsulate the data access for that module within the database context. The other modules don't have a way to access this database context, and we are also enforcing a custom schema for our modules by configuring the ticketing schema in this example. You will also notice that all of the database set properties are internal, and they are only available from inside of the infrastructure assembly of the ticketing module. And we could even make the database context internal. The only reason this is public is so that we can easily apply database migrations during application startup. Another thing that you will notice for our database contexts is the presence of a unit of work interface. Now, if I look for this type, you can see that I have 4 definitions of the same interface across my modules. And you might ask yourself for a moment, why are we duplicating the same interface across multiple modules? For example, here's the unit of work in the users module, and then we have the same interface in the events module, for example. Isn't this pointless code duplication, or is there something more to it? The main reason that we are forced to do something like this is because of how dependency injection works in ASP.NET Core. We only have one composition root, and if we were to share the unit of work interface across our modules, then how would we know which of the implementations of this interface to resolve from dependency injection, given that this interface is implemented by the respective database context of that module? So in this case, we are using code duplication to encapsulate the implementation details, in this case of the unit of work, inside of the respective module. I also mentioned that we are using schemas, so let's take a look at an example query like the getOrder query handler, and I wanted to comment on the SQL query that we are writing to fetch the required information. You can notice that our queries are also referencing the respective schema, which is another way how we can enforce logical isolation between our modules. We don't allow queries across schemas that aren't in the current module, and we could even write a custom code analyzer that would scan the code in a given assembly and make sure that there are no queries referencing the schemas of other modules. That would be the compile time approach to achieve something like this. We can also achieve the same at runtime by using different connections for different modules, but having to run your application to only then realize that you have a problem isn't really ideal. Another thing that we are doing across our modules is defining a single point of entry for configuring dependency injection, configuration values, and message consumers, and this is the respective module class. They all follow the same structure, and this allows us to easily integrate the respective module into our runtime application. So using techniques like this, where we encapsulate a given module within a few assemblies, making the most that we can out of the internal access modifier, duplicating code across our modules, and allowing a single point in entry for dependency injection configuration. We are also doing the same for our application settings or configuration values, where we have dedicated settings files for each of our modules so that we can easily distinguish the configuration between our modules. And one last thing that we are doing is duplicating the data across our modules. For example, in the ticketing module, we have the concept of a customer inside of our domain, which also represents the user inside of the users module. And this is both an implementation of different bounded contexts across our system, but also another way for us to enforce modularity. And with this, I'm going to slowly wrap up the discussion about designing a modular architecture. I think all of the lessons that we have covered before this one also contribute to the same topic, so I don't want to repeat myself too much, but I do want to highlight that we are making the most that we can from the constraints that we have available to us in C# and .NET. Now let's wrap up this lesson and continue to the next lesson, where I'm going to show you how to write architecture tests to enforce your modular monolith architecture.